Okay, so we talked about this, one of the technologies for implementing and adding and really leveraging these real-time HIL models as part of a physical test cell. And there's some other technologies. I mentioned that part of a big part of my role is helping to influence the investment that we make into the tools. And one of the major investments that NI is making is into a software framework that can be used for creating these real-time testing applications. And so if you think of all of the real-time testing applications, and here's an image that we use sometimes to describe how you've got the MIL, model in the loop, and hardware in the loop, and other software validation techniques which require a real-time test environment, as well as the more traditional test cells, dynamometers, and environmental chambers that require a real-time test environment. And then these blended versions where we're now using models with physical control, such as model-based dynamometers or component-in-the-loop simulators. And if you think of all of these applications, there's really a common set of functionality that is necessary to implement them. And whether it be real-time, point-by-point hardware I/O, support for the modeling environment that you need to implement the simulation, and so on. And so NI Veristand is a product that we are investing in and have created to provide out of the box those features inside a well-tested, high performance architecture for implementing these types of software applications. And so primarily over the last 4 years, Veristand has been used on the left side of that spectrum. It's been used to do hardware-in-the-loop simulation, model-in-the-loop simulation, some rapid prototyping, evaluation test systems. But I think we're about 3 weeks away to, ask Roy if you see him, if you want to know, but in 2 to 3 weeks, we're going to be happy to announce that National Instruments is going to be reselling the Inertia product from Wineman as an add-on to NI Veristand. And this is really going to be a great marrying of technologies because there was some overlap in the capabilities that were being maintained simultaneously by our engineering group and the Wineman engineering group. And so what we're doing is we're optimizing how we together invest our resources for this application space. And so Inertia will now be available as an add-on to NI Veristand to expand it beyond hardware-in-the-loop testing applications, but into these more mechanical simulation, such as dynamometers or servo-hydraulic-based test systems. Okay, so for those of you, I don't know that everybody in this room is familiar with Inertia, and if you're not, I can say I think you should be, because it's a product that's been out for quite a few years. It's owned by Wineman, and it's used to implement test systems that have multi-axis or multi-actuator control systems. And I won't go into all the details. There's plenty of demonstrations in there that could show you that, but they've, over the years, many years of refining this product with customer feedback, have a really nice, really reliable way of implementing these test cells. And you could talk to Darren or Brian or Tim or any of these guys, and they could tell you stories about the fastest RPM or the most torque. Or I love hearing their stories of what this software has been able to accomplish. So one benefit, other than some of these other stuff, one of the benefits of the marrying or the merging of these technologies, though, is really to enable you to very easily implement the test systems that I was just describing, to leverage those hardware-in-the-loop models that have had a great investment over the last decade and have a great amount of power, sophistication that you can bring to your test cells. And all of that is provided by Veristand. And National Instruments has been investing in that technology since models started running in real time. And so we've got a really well worked out process for bringing those models in from any environment on this list you see here, and linking them to real-time I/O, to user interfaces, and enabling this real-time simulation interacting with the real world. And so with the addition of Inertia to Veristand, now we bring the control that's necessary to implement the mechanical portion of that simulation there. So I have one disclaimer to make, though, just to, in case any of you are existing Inertia customers. Wineman is not stopping the availability of Inertia as it is today, and they are also offering a service to upgrade your existing standalone Inertia application into the next version, which is based on top of NI Veristand. So you can talk to one of the Wineman guys after this if that's something of interest to you. Okay, so then I'd like to wrap up with just one other trend that we've been seeing growing in its usage to address some of these challenges. And really that is the increasing the test component reuse throughout the process to increase the quality of a product and increase the efficiency of the development of that product. All right, so to tell you a little bit about what I mean by that, I don't know how many of you here have followed the National Instruments Automated Test Outlook. It's a publication we started in 2009, 2010, and it's where some of our technical leaders and fellows and vice presidents, they look at the industry from the vantage point that we have as a broad-based test tool provider, and they look at what they see in the next 2 to 3 years being the trends that will happen. And one of those was talked about in 2010, which was this blending of design and test. And essentially what our VP of engineering, what he was quoted as saying is that engineering teams will need to start viewing software and hardware test components as a common DNA that persists throughout the entire development process. And if you didn't read this article, the next few slides here, I'll explain to you what he meant by that. Okay, so effectively when you're building a mechatronic system that uses embedded software, you commonly are going to be referring to this V diagram or this V cycle that is used to describe that development process. And there's a million flavors of them out there. Everywhere I go, there's a different flavor. This is one I've come up with that seems to be the most kind of catch-all, simple one, and it's effectively on the left-hand side, you're designing the software and the necessary mechanical components to achieve your requirements for control. All right, and then in the second step, you're going to go and you're going to be prototyping that. Oftentimes, you're going to have not a deployed embedded software ECU, but you're going to get a rapid prototype, a real-time PC, and connect it up to a prototype of the system and evaluate what the ideal world implementation or algorithm looks like implemented in a real world when you add A to Ds and discrete time and other limitations that we have in the real world. All right, and then at the very bottom, you get to what's called deployment, and they make the V because you're crossing over now. You don't want to come back, because you've taken all the effort to take that algorithm, refine it, put it down onto the embedded controller, and have this cost-optimized, performance-optimized implementation that you intend to ship with the product. All right, and so then you start working your way back up the right-hand side where you're going to perform hardware-in-the-loop simulation or validation, which we talked about earlier, and physical testing. So that could be bench-based testing or test cells or out in the field in a proving grounds or just field-based testing. And so what we've seen is it traditionally, let's say 8, 9 years ago when I was out here in Michigan, I'd always heard it talked about as the left is design and the right is test. And there's been a different philosophy in the way that this V diagram is being viewed, in that now engineering teams are recognizing there's testing going out throughout the entire process. Okay, early on when you're designing it, you're doing what's called pure simulation or model-in-the-loop testing of your system. So you still got stimulus and you're still logging data and visualizing data. You're just doing it all at your desktop in a simulated environment. And really that prototyping, when you build that prototype, well, that was typically thought of as the design phase of prototyping the controller, but really you have to test that prototype, and so you need a test cell or a hardware-in-the-loop simulator here to perform that evaluation of your prototype. And then at the bottom there's a technique commonly used and more frequently being used called software-in-the-loop testing. So here you look for errors in translation from model-based equations for control to C code or actual machine code that's being used to implement that on your hardware. Okay, and so this first change or shift that I've seen where the view of the V diagram is that there really is testing going on throughout, then identified that this is being done in silos in most places today. You've got the development team, the modeling team that does testing here, and then they hand over their deliverable to the next team, and the next team builds up their test, and then they hand over their deliverable to the next team, and they build their test, and so on. And at each one of those silos, at each one of those places, there's test components being recreated, oftentimes the same, and I'll argue even worse, oftentimes slightly different test cases that are being created at every phase in the V diagram. And so you've got your user interface, you've got your stimulus and logging profiles, you got your linkage back to your requirements so that you can verify that you're getting complete coverage of what you intended to do, your models themselves, and so on. So all those components are being recreated. And so essentially what was happening is as you progress through the V diagram, there's different real and simulated parts of the system being swapped out. So you may start out and it's purely simulated, but as you progress over to physical test, you're replacing models with physical components. linking them to the simulation through either electrical or mechanical simulation. And so the real opportunity that several of our customers have been embarking on is to establish a process of reusing those test components. And really, it's a shift in thinking, and it's not a simple task. It requires a change in philosophy of how these groups operate and defining ways to transition these components from step to step. But what we're finding there with some of these customers as they begin to achieve part of this vision here in the last year is that they're now being able to get much better correlation between their early test and what they thought the product was supposed to do, and then what actually ended up happening in the test cell or out in the field testing there. So they can look at the data the same way. They can be more efficient in the way they create their test. So maybe the person down the line doesn't need the same exact test, but they can sure start with the test that was done in the previous step in the development and then refine on that. And there's been, in many cases, if you want, I can talk to you about it offline, where PLM tools and configuration management tools are being used to really add another level of organization on top of this. And the end result is, to the company that's applying this concept now, they're being more efficient in the way they go through this process from a validation standpoint. And they're finding that they are being more accurate in their decisions and ultimately producing greater quality because they're looking at results the same way at every step. So the test cell engineer looks at the results that we're doing on the dynamometer and compare them to what was done in simulation. And they can identify, did we have an error in translation as we moved from a model to actually deployed code? Or was my plant model not accurate? And do I need to refine my plant model so that the next time my design engineers begin a project, they have a more accurate representation of what it's going to be like when it gets down the road here to me in the real world? All right, so I had a few more slides that kind of illustrate technically how this is done using Veristand and inertia. But I think in the interest of time, because there's a lot of good demonstrations back there, what I would like to do is I'll just jump to the conclusion here and allow you guys to get on to checking out all the wonderful stuff that Wineman set up for you here today. But in summary, I hope today maybe a little bit of what I've shared with you from my experiences I've had with different customers in different industries is the real opportunity here to leverage the investment that's been made into real-time models because of the need for agile testing, and to leverage that now in your physical test cells to really evolve those physical test systems to be able to adapt to the challenges that you're either already experiencing or that are coming in the future. And then secondly, for those of you that are working in systems that are dealing with embedded software controlling these mechanical systems, we've got much more I could talk to you about on how Veristand and Inertia and these products really ease the transition to a process where test components are viewed as assets to the project that are reused throughout the entire process to provide higher quality and greater development efficiency as you try and balance the quality expectations with the timelines and the budget demands. So with that, Wineman, thanks again for having me here, and thank you all for your attention. I'd be happy to talk with anybody afterwards too.